We also discussed the topic of inline material analysis in the area of straightening. Maybe we can also use our micromagnetic method, which we will hear more about later on, in straightening processes to get further insights. We have been working on pattern recognition and signal clustering for quite some time. I already announced it. In straightening processes, signal clustering is of particular interest to us, but it has not yet been included in the new interface. But Elias might show us what the next steps could be.
Yes, I hope so. Ulrich already mentioned at the beginning of this presentation that we have also changed our perspective on our work. This naturally includes the fact that we are dealing with more and more equipment with ever-increasing amounts of data, and of course we must somehow think about how we want to do this. So we had already heard something about plastic injection molding. It was about 97 different signals per process and then hundreds of thousands of processes. This is quite a number. In straightening processes, the signals are less frequent, but nevertheless, over the years in series production, thousands and thousands of signals accumulate, and they are quite different. So there are different signal types. These include, for example, different types of crack signals in straightening, but also different noises from the machine, which should be evaluated as disturbing noises and therefore should not lead to the component being rejected. But you shouldn't believe that once everything has been beautifully adjusted by our service technician that it will run smoothly and will always behave so well for years to come. Because of course the machine's environmental conditions change and also the machine changes a bit. Maybe the machine will be used on the other side of the world and the situation is slightly different. That means that we somehow have to constantly learn to adapt to the process and to optimally adjust our analysis to the circumstances. And this is why we are now heading there and use machine learning more frequently to prepare our measuring equipment to automatically adapt and to improve constantly. So one method that we have now implemented in this context is clustering. It involves, we saw this briefly in the video earlier, collecting various signals. Then we get these rectangular boxes in the landscape, but this is the uninteresting part. In the end, we get an overview of a lot of signals where you can already see with the naked eye that they have some similarities. So somehow there is a pattern in this data, and of course we always try to find it. This is the actual idea behind pattern recognition, which we have been using successfully for many years. But it cannot automatically adapt to the circumstances. This is the point where clustering comes in. Clustering is a precise attempt to identify the similarities between data. So we analyze the data. We compare all these signals with each other and find out what are the properties that these signals have in common and which properties differ significantly between the different groups of signals. And so we end up with groups of, for example, noise signals that look super similar. They have very similar signal characteristics, but differ strongly from, for example, the group of crack signals. And that is exactly what clustering does. So we find out what the similarities and differences are and can group signals fully automatically. Well, I did that on 1,000 signals the other day and it took me about an hour to do it. And that is a very manageable time frame within human power. We evaluated 1,000 signals completely one after the other and thus automatically determined groups of new signal types that we might not have been able to detect at all before, as the service technician might not have seen this signal when he was working on the machine and setting it up. Exactly, so it was simple to distinguish between these signals.
It was simple? How long did it take to program the clustering until it ran smoothly?
Yes, hold on. Well, that was a classic C++ solution, so I would state a time period of months to years. The difference between these signals and those signals is quite noticeable. In this respect, I just meant that it is simple to recognize the difference. However, I mean, the algorithms behind the clustering are able to point out smaller signal differences. Here, for example, we already see many similarities between these signals. But if you take a closer look, you will notice that we already have different signal types. It is not one and the same signal. Clustering takes care of that as well. So I mean that we now automatically get a grouping of these signals, and based on these grouped signals we can then create a new pattern. This is done by merging these signals and at the end creating a representative for this group. One might call it a golden sample. So it is a pattern that represents as well as possible the various signals that are grouped together and which must be very similar. And you can feed this pattern back into pattern recognition and thus improve our analysis even further. Of course, this also improves the decision for the respective component in the end. That is the goal of all of this. This means that in the end, as Ulrich has already said, not everything runs automatically yet. An assessment of the signal must be made. But it no longer involves that the operator or even the service technician has to stand in front of the system and click through thousands of processes manually. Instead, we have, as in this case, perhaps 4 or maybe even 20 different representatives of groups afterwards, which are then assessed accordingly, and for which it is determined this part was okay and that part was not okay. This can of course happen in connection with the laboratory analysis. However, we plan to implement this in such a way that we can also make suggestions based on larger database libraries of signal patterns that we already know. But it has not yet been implemented this way. And these insights can of course be fed back into pattern recognition. Then we can identify matching patterns and we can not only say there is something, but we can also say what it is. So that we have exactly recognized this particular signal pattern there. So that the situation is obviously similar and we can adjust our decision to what is exactly happening in the process. And the cool thing is that it works automatically. You do not have to spend hours and hours to manually sort signals, but you can quickly get the machine to adapt itself further and further to constantly optimize through our analysis.
Thank you, Elias. Elias, can we do this while the machine is operating, when it is in use at Volkswagen or Daimler?
That is definitely the plan. Actually not yet today, but I would say that it can be implemented within a few days.
This means that the measuring system would then be able to recluster and learn new patterns while measuring in process?
Ultimately, the idea, in accordance with all these interface concepts that we have already seen, is that we also insert a new page into the interface where the operator automatically and again receives propositions for signal patterns to evaluate. So in the end, the operator no longer has to go to the machine and say, I want to optimize now, but the machine says, I have identified something here, please give me feedback. This way we can also change the direction a bit and thereby achieve that optimizations are actually carried out.
So part of our way are machine learning and automatic measurement.
Exactly. With pleasure.